Welcome, students, to our remote learning program for AP Chemistry. Today, we're going to actually begin Unit 9.7. On Friday, we finished 9.5 and 9.6 and our discussion of delta G. So when we begin this talking about galvanic cells, we're actually talking about a battery, and there's a lot of chemistry that actually goes on inside of a battery, and these reactions are actually half reactions. We're going to start to study and look at how to do calculations with this. So first off, a couple of terms. Galvanic, also known as voltaic. That's another term that you will come to associate with batteries. There's something called electrolytic that we'll talk about a little bit later on. So first off, these reactions that take place in galvanic cells are redox reactions. Now, we studied redox reactions earlier in the first semester. And to begin with, I want to just review a little bit and look at what a redox reaction is. So I'm going to write here for us a couple of things. So first off, let me write this here. So I have aluminum plus copper 2 plus reacts to form aluminum 3 plus copper. So when we look at this, to balance this, you actually have to use redox. So these already have their oxidation numbers assigned to them. We know that a solid is 0, and I'll put a 0 here. This is a 0 on this side as well. So when we look at this, we see very quickly that the copper's charge is reduced. So this is reduced, and then when we look at the aluminum right here, it is oxidized. So knowing that, we can actually begin the process of writing our half reaction. So what do we have here? We have aluminum, which is Al, and we're going to put our arrow, and that's going to form aluminum 3 plus 3 electrons. That's what it had to lose to get that 3 plus charge. The next one we can look at is our reduction. So we have here our copper, and that is Cu2 plus, and it's going to gain plus 2 electrons, and that's going to produce copper. Hopefully some of this might be coming back to you. So now we have to look at our electrons, and we have to balance them to cancel on each side to 0. So I'm going to just draw my line here. And when I look at 3s and 2s, I know that 6 is the common factor. So I'm going to multiply this top one by 2 and this bottom one by 3. So now I'm going to get 2 aluminum plus 3 copper 2 plus 6 electrons. Now I get my arrow, and I get 2 aluminum 3 plus 6 electrons plus 3 copper. So now to balance this equation, I can look on both sides and look at what can cancel. Well, I've got 6 electrons right here, and I got another 6 electrons here. That can cancel. So now to write the balanced equation for this redox reaction, I have 2 aluminum plus 3 copper 2 plus reacts to form 2 aluminum 3 plus 3 copper. So if we look at this, both sides balance. We have 6 positive on the left reactant side, and I have 6 positive on the right, and our atoms all balance. So this is our redox reaction balanced equation using half reactions. And that's what we have to do and learn to use when we talk about galvanic cells. So let's flip the slide here, and let's look at another one, maybe one that's a little bit more complex. But first off, oxidation. When we think about oxidation, remember, oxidation is the electron loss. And then reduction is a gain in electrons. Those are just a couple things that you should try to remember. So let's look at another half reaction. When we talk about a galvanic cell, we're going to be dealing with acid solutions and base solutions. So the H plus and the OH minus. Hopefully you remember that. You have good notes from that section. I would probably advise to look back on that. So let me write another reaction right here for us. So I have manganese oxide, and this is a minus charge, and I have plus iron, Fe, reacts to form iron 3 plus manganese 2 plus. So the first thing I have to do is identify my oxidation numbers. So we know this oxygen is a 2 minus, so this is going to give us an 8 minus on this side, meaning this manganese must be a plus 7. Iron in its natural state of solid is 0. We have a 3 plus on the next iron and a 2 plus on the manganese. So when I look at this right away, I see the manganese charge is reduced. Right here is reduced. And when I look over here and I see my iron to 3 plus, means it is oxidized. So now I can write my half reactions for this. So first off, starting here with my iron, I'm going to go Fe. I'm going to write my arrow right here, and I'm going to have Fe3 plus 3 electrons that are lost. The next thing I have is my manganese oxide. So I'm going to go MnO4, and that's minus. And I'm going to come over here and put my arrow, and that's going to have the Mn2 plus. Now, if you remember, on this left side, the reactants, I have 4 oxygens. So I'm going to have to produce those oxygens, and it's used by water. So I'm going to go 4H2O. Now I have to account for these hydrogens as well. So I'm going to come over to this side here. I'm going to go plus 8 hydrogens. Now I have to count my electrons on the reactant side. So my manganese went from 7 plus to 2 plus. That means it gained 5 electrons. So I'm going to come over here. I'm going to go plus 5 electrons. So now I am able to try to balance this redox reaction. So first thing, I'm going to draw my line here, and I got a 5 and a 3. The common factor has to be 15. So I'm going to put my parentheses, and I'm going to multiply the top by 5 and the bottom by 3. So now I'm going to have 5 iron plus 3 manganese oxide plus 15 electrons plus 24H plus. Now I can have my arrow. Now I'm going to have 5 Fe3 plus 15 electrons plus 3 Mn2 plus plus 12 water. So now I'm going to look at what can I cancel off of each side. And when I look at this, I have 15 electrons here, 15 electrons on the product side. I can cancel them. So now I'm going to write my final balanced equation in an acid solution. You're going to notice that here in a second. So I'm going to go 5 Fe plus 3 manganese oxide plus 24 H plus reacts to form 5Fe3 plus 3Mn2 plus 12 water. So that is my balanced redox reaction in an acid solution. So remember, please, that if this was in a base, I calculate my acid first, and then in this case here, I'd multiply both sides by 24 hydroxides. And that's the difference when you do an acid from a base solution. So I have a little practice for you assigned in RenWeb as homework. So please take advantage and take a look at that. And I believe I have it due on Friday to be dropped in the Dropbox. So now let's move on. So we have reducing agents and oxidizing agents. So reducing agents lose electrons, oxidizing agents gain electrons. And then we have X is oxidized by Y, becomes more positive, and Y is reduced by X, becomes more negative. So please take a look at this PowerPoint slide here. Maybe jot this down into your notes and look that over. All right, so here is a first image of a galvanic cell. So this shows us that we have some electrodes that are going to be in some solutions. You can see the electrode, one is zinc and the other one is copper. And you can see the flow of electrons. It shows arrow showing the electron movement. You see this salt bridge right here, and we're going to talk about salt bridges a little bit more. And then you see the solution. And that is how these galvanic cells work. So what I want to do is I want to build a little bit on this right here, and hope you get some good notes on this and try and show us exactly what is happening in this situation. So I'm going to change the slide, and I'm going to begin the process of labeling. So what I'm going to do is I'm going to label this as zinc. So I'm going to come over here and I'm going to put ZN, and that is solid zinc. And over here, we're going to have Cu, and that's solid copper. And we're going to place that in this container. So we have our salt bridge, which is made of a porous gel-like material. And that is what is inside what's connecting both the liquids, and we'll talk about that a little bit more. So let's just say this liquid right here, let me put an arrow right there. This is zinc sulfate, SO4. And over here, this solution is copper sulfate, CuSO4. So now we're going to look at what is going to happen here. So we have our anode. So what is going to happen here is this zinc in the solution is going to lose 2 electrons. So we're going to write a half reaction right here. So we're going to have Zn is going to produce Zn2 plus 2 electrons. So this is what is happening right here. And this is our anode, as it says right here. So the zinc on this plate, this metal plate right here, is losing 2 electrons. As you can see, the electron motion is going to be coming this way, and that's the 2 electrons that this zinc lost. it is going to leave the zinc plate and go into solution as zinc 2 plus. So you could say the size of this zinc right here is diminishing. It's shrinking. So the electrons are going to travel across. You can follow this. You could have a light right here. You could have a voltometer or something to measure. But what is going to happen? We're going to come over to this side here, and the electrons are going to travel down into this, through this copper plate, down into the solution. What is going to happen is inside here, we have Cu2 plus ions in solution right here. They are going to accept those 2 electrons. So they're going to become a solid and build on that electrode. So on this side here, we have Cu2 plus 2 electrons, resulting in solid copper production. So this is what is happening on this side. So this is being reduced, and the zinc is being oxidized. So now you could say that this copper is becoming thicker because more and more are going to adhere. More and more the copper ions are going to lose their charge by gaining the 2 electrons and plate. And that's also how electric plating works, just as a side note. So this salt bridge, so this is what's causing this flow to happen. If we did not have this salt bridge right here, this reaction would only run a little while and then it would have to stop. What ends up happening is we end up having the sulfate ion, SO4 2 minus, leave the solution because this side is becoming more and more positive. It has to leave this side here. Let me correct myself on that. It's becoming more negative because the copper is being reduced and the charge is being reduced. So in order to not have a buildup of negative charges on this side, this SO4 2 minus is going to leave and go across this bridge and enter the solution on that side. So when you look at what's happening on the side that's being oxidized, so you're getting a buildup of zinc 2 plus. So in order for this to not become just full of zinc 2 plus ions, they are going to actually cross the salt bridge to the other side. So that is what does allow this reaction to continue, is by the charges balancing by going to the opposite side so that the reaction can continue and it flows through the salt bridge. If you did not have the salt bridge, it would only run for a little while and it would stop. All right. So when we look at this galvanic cell definition, it's a device which chemical energy is changed to electrical energy. We talked about that. Oxidation occurs at the anode. You want to notate that on all galvanic cells, this is what's happening. It's going to be a little different when we talk about electrolytic cells. Reduction right here takes place at the cathode. A little phrase, cat gets fat, cathode gains electron, reduction. So those are just some little ways to try and help you remember, but that's a very important point right there. And here's another disc, and here is another, it's called a porous disc, is another example of a salt bridge. And this is just in a different format. Once again, here is a galvanic cell, and this time it is labeled for us. And you can see that the magnesium strip and the silver strip are in solution. Here we have magnesium nitrate. This side we have silver nitrate. And you can see what's happening. The magnesium is coming off and becoming aqueous as Mg2+, and the electrons, 2 of them, are flowing. So we could say 2 electrons are flowing. Could be a light at the top here, could be a voltmeter, should be any of those things that can pick up the charge. The electrons are going to flow through this silver into the solution, and what's going to happen is the silver is going to become plating against that metal and become thicker. And what's going to happen now is the nitrate is going to move through the salt bridge, as you can see right here, and on the other side we have the sodium coming across from the salt bridge itself. So we're having it replaced with the magnesium, and then the sodium is going to come out. So the magnesium is going to come in this side over here, Mg2+, and in this salt bridge, the Na is going to flow out. And that will help this to continue until this magnesium anode is gone. When it's gone, the reaction is over. Here is another look at the same reactions we've talked on, just another view of it. And ladies and gentlemen, that is it on this particular lesson. What I want to leave you with, if I could, is the half reaction that we talked about. So we have our zinc, and it is becoming zinc 2+ plus 2 electrons, and then we have our copper, Cu2+ plus 2 electrons, and that is going to form solid copper. If I was going to balance this, I have my electrons cancel on each side, so I have here, I could write zinc solid plus copper 2+, and this would be aqueous. And I have my arrow here. I have my zinc 2+, and now that is aqueous, plus my CuS, my copper solid, which is plating on the other side, on the other electrode. And we will begin the process of, on my next lesson, my next virtual lesson, is how to calculate the standard reduction potential, or the volts is another term for that, given this redox reaction and the half reactions. All right, thank you for watching, and stay tuned for our next virtual lesson.